In the early 1980s, it seemed like computers were speeding up every year simply by cranking the clock faster. But behind the scenes, engineers could see the ceiling coming. Pushing a CPU's clock speed meant signals had to cross the chip in ever shorter fractions of a nanosecond. Wires became transmission lines, power draw soared, and heat piled up. You can't cheat the speed of light, and on a few square centimeters of silicon, that limit was starting to bite. At the same time, fabrication technology was racing ahead. Suddenly you could fit far more transistors onto a chip than traditional designs really knew what to do with. Classic complex instruction set processors, the big CISC chips, were hitting a performance plateau even as the silicon budget exploded. The broader landscape didn't obviously demand a radical new approach. Mini computers from companies like DEC and Data General still ran much of the world's business computing. The IBM PC, launched in 1981, was just beginning to find its place on office desks. Apple's Lisa in 1983 and the Macintosh in 1984 introduced graphical user interfaces, but their Motorola 68000-based hardware struggled under the weight of bitmapped graphics and new operating systems. They were elegant, but often felt slow and underpowered. Parallelism, many processors working together, was an old idea that suddenly looked like it might be the only real way forward. If you couldn't make one CPU dramatically faster, perhaps you could use 10, or 100, or 1,000. In that climate, a small British company decided not just to tweak existing designs, but to bet everything on a microprocessor built, from the ground up, for parallel computing. In 1978, the British government helped fund a new semiconductor venture based in Bristol, INMOS. The idea was to give the UK a serious foothold in advanced chip design at a time when the industry was increasingly dominated by the US and Japan. Among the engineers at INMOS was computer scientist David May, working with Robert Milne and a small ambitious design team. Their remit was not to produce yet another general-purpose microprocessor, but to explore what a chip would look like if it took parallel computing as a starting assumption rather than an afterthought. They called their creation the Transputer, a portmanteau of transistor and computer. The name hinted at the role these chips were meant to play. Just as transistors had once become standardized building blocks for constructing computers, transputers were meant to be the new building blocks. Self-contained computing nodes that could be wired together in large numbers to form a complete system. The original vision was strikingly broad. A transputer would be cheap enough, at least in theory, to cost only a few dollars, and flexible enough to be used anywhere, as the main CPU in a workstation, as the controller on a disk drive, or as a node in a massively parallel supercomputer. In a conventional design, the processor on a disk controller sat idle whenever the disk wasn't active. In a transputer system, every spare cycle on every chip could in principle be put to work. This was Bristol's Gambit. Instead of one giant central brain, build a society of small identical minds, all talking over simple fast links. To make this vision real, the transputer's architecture broke from the norms of its era. First, each chip was designed as a largely self-sufficient computer. A transputer included not just the CPU, but a block of on-chip RAM and an integrated memory controller. You supplied power and a clock, and for many tasks, that was enough. This processor and memory feel made transputers behave a little like powerful microcontrollers, well before that term was fashionable in desktop computing. Second, the chip abandoned the traditional shared bus in favor of built-in communication links. A typical transputer had 4 high-speed serial links, configurable at roughly 410 or 20 megabits per second. These point-to-point links could connect one transputer directly to its neighbors, forming rings, grids, cubes, or more exotic topologies. They weren't just for data. A chip could actually boot over a link, loading its code from another transputer instead of from local ROM, which made it easier to build large, flexible networks. The CPU core itself looked nothing like the growing crop of RISC processors, such as MIPS or ARM, with their banks of 32 general-purpose registers. A 32-bit transputer had only 6 registers, a workspace pointer for locals, an instruction pointer, an operand register, and 3 registers called A, B, and C that formed a tiny evaluation stack. Most arithmetic instructions operated implicitly on this ABC stack. Loading a value pushed the stack down, Storing popped it up. That sounds Spartan, but it was deliberate. With only a handful of registers to save and restore, the processor could switch between tasks at very high speed, crucial when you want thousands of lightweight processes to share a chip. The instruction set itself was compact and regular. Each instruction was a single byte, 4 bits of opcode and 4 bits of small operand. Special prefix instructions let you build larger operands from multiple bytes. Combined with the fast on-chip memory and simple data paths, this design supported hardware-level process scheduling. Many applications could run directly on the bare metal without a conventional operating system at all, relying on the transputer to multiplex processes and manage communication links. Hardware alone wouldn't make parallel computing approachable. INMOS paired the transputer with a new high-level language, Occam. Occam was based on the ideas of communicating sequential processes, CSP, developed by Tony Hoare. In Occam, you structured your program as many small, independent processes that interacted only by sending messages down channels. That model mapped almost directly onto what the transputer hardware provided: lightweight processes scheduled in hardware, and links that behaved like channels between chips. In an era dominated by sequential languages such as C, Fortran, and Pascal, this was a demanding shift. Occam was deliberately strict. There was no shared mutable state, no casual global variables. Synchronization and communication were explicit. For researchers in concurrency, it was exhilarating. For working programmers, it often felt alien. This tight co-design of language and hardware gave the transputer some of its elegance. When you wrote in Occam, you were programming almost at the level of the chip's mental model. But it also became a barrier to adoption. Many potential users wanted to reuse existing C or Fortran code, and compilers and tools for those languages lagged behind the Occam toolchain. Plenty of people admired the idea of the transputer, yet bounced off the reality of learning Occam and an entirely new way of structuring programs. The first transputers to reach customers formed a small but carefully tiered family. At the low end was the 16-bit T2 series. The early T212 provided 2 kilobytes of on-chip RAM and clock speeds around the high teens to 20 megahertz. It lacked some of the more advanced scheduling hardware of later chips, but it proved that the architecture was viable in silicon. Successors like the T22 and T25 added more RAM and hardware breakpoint support for debugging. The real breakthrough came with the 32-bit T4 line. The T414, announced in October 1985, delivered a full 32-bit core, 2 kilobytes of on-chip RAM, the 4 communication links, and clocks in the 15 to 20 megahertz range. A later refinement, the T425, doubled the on-chip RAM to 4 kilobytes, added more instructions, and made debugging easier. For number crunching, the 32-bit T8 series took center stage. The T800, introduced in 1987, extended the instruction set and, crucially, integrated a 64-bit IEEE 754 floating point unit on chip. That combination of parallelism, fast floating point, and integrated memory made the T800 the workhorse of serious scientific and engineering applications. Around these CPUs, INMOS shipped a constellation of support chips. The C011 and C012 link adapters let you bridge a transputer's serial links to an 8-bit parallel bus, so you could plug transputers into more conventional systems. The C004 link switch was a full crossbar connecting up to 32 links, enabling complex and even reconfigurable network topologies at the board or system level. Taken together, the T2, T4, and T8 families provided a ladder from embedded control through workstation-class computing to parallel supercomputing, all built on the same basic architectural idea. Transputers did not remain lab curiosities. Through the late 1980s, they found their way into a wide range of real systems, especially where parallel workloads were natural. In high-performance computing, British company Mako built the computing surface, a modular machine made from boards studded with T800s and external RAM. A single board might carry 4 T800 transputers. A cabinet could contain many such boards, plus I/O modules, forming a desk-side supercomputer. Larger installations chained multiple cabinets together for serious number crunching, while still presenting a relatively compact footprint. Across Europe, the ESPRIT supernode project used networks of transputers as a platform for research into parallel algorithms, network topologies, and new software models. It was as much a laboratory for ideas as it was a computational resource, and it helped cement the transputer's reputation as a serious tool for advanced computing rather than a boutique British curiosity. Industry quietly adopted transputers in places where their strengths mattered: digital signal processing for telecommunications networks, synthetic aperture radar processing, and other real-time systems that benefited from deterministic communication and fast floating point arithmetic. Some experimental desktop systems offered transputer-based accelerators or workstations, promising personal access to parallel computing. The underlying allure was simple and powerful. If you needed more performance, you didn't have to redesign your whole machine. You added more transputers, wired in via their links or through a Caesar 4 switch, and scaled out your software. In an age before multi-core processors, this felt like a glimpse of a possible future of modular, scalable computing. By the end of the 1980s, however, the competition was not standing still. Conventional microprocessors were adopting pipelining, on-chip caches, and eventually multiple cores. To stay ahead, INMOS planned a bold new generation, the T9000. Built as the successor to the T8 line, the T9000 aimed to marry the transputer's parallel strengths with the raw, single-chip performance of the latest RISC and CISC processors. It featured a deeper 5-stage pipeline and a sizable 16-kilobyte cache, far more than earlier transputers. Its communication system was redesigned around 100 MHz packet-based links, a massive jump over the tens of megabits offered by the original OS links. At the heart of the new design was the Virtual Channel Processor, or VCP. Earlier transputer programs often needed to be aware of the physical network layout. Which chip talked to which neighbor? The VCP promised to decouple software from that topology. It would map many logical channels onto a smaller number of physical links, handling routing and flow control in hardware. In theory, programmers could think in terms of abstract channels and let the T9000 fabric sort out the messy details. On paper, it was everything fans of the architecture had hoped for. In practice, the project ran into severe trouble. Implementing the VCP and high-speed links proved much harder than anticipated. The chip's complexity ballooned, performance targets slipped, and debugging the design consumed time and money. Meanwhile, INMOS itself changed hands, from state ownership to Thorn EMI, then to SGS Thomson, adding corporate uncertainty to the technical risk. By the time early T9000 parts trickled out in prototypes, mainstream processors had surged ahead in clock speed and price performance. Workstation and server vendors were standardizing on more conventional multiprocessor and, soon, multi-core designs. The T9000 never reached the volume or maturity it needed, and with its failure, the commercial transputer line effectively came to an end. There's still some debate about exactly how much was technical overreach versus business mismanagement, but the outcome is clear. The grand British experiment in building computers from swarms of tiny linked processors faded from the market just as the ideas behind it quietly spread elsewhere, in message-passing supercomputers, network-on-chip designs, and eventually in the multi-core CPUs, now found in almost every device.